hope you had a little bit of a break and are ready for our next session, which is we have a pair of very esteemed speakers. The next session is a fireside chat that will provide some perspectives on quantum information science and engineering, particularly for the telecom industry. So this session is going to be hybrid. Our moderator, who's here with us in the room today, is Monisha Ghosh. She's research professor at UChicago and incoming professor of electrical engineering at the University of Notre Dame. She recently completed a term as a chief technology officer at the US Federal Communications Commission, where she reported to the chair of the FCC and was closely involved with setting national strategy and tech specifications related to broadband wireless communications. She conducts research on wireless technologies for 5G, cellular, next-gen Wi-Fi systems, IoT, coexistence, and spectrum sharing. She's previously worked in industrial R&D at Interdigital, Philips Research, and Bell Labs on a variety of wireless systems. And also joining us today virtually from the UK is Andrew Shields. Andrew leads the R&D and business development for quantum technologies in Toshiba Europe. He's published over 500 highly cited research papers and patents in the field of quantum devices and systems. He's a member of the leadership team of OpenQKD Consortium in Europe and the EU Strategic Research Agenda Working Group. He was a co-founder of the industry specification group for QKD for the European Telecom Standards Institute, also served as chair for several years. In the UK, he leads the Aquasec project developing next-gen quantum communication technology. He's a fellow of the Royal Academy of Engineering and was awarded the Mott Medal and Prize for research on quantum photonics and applications. So without further ado, I'd like to turn it over to our speakers.
Welcome to what I think will be a very interesting discussion. There he is. Andrew is an expert on quantum technologies, and he's going to walk us through some of what the promises and challenges of applying quantum technologies to communications in particular is. I am not an expert in quantum. I have spent my career working in wireless. But just to put it into context as to why it's important to have this discussion now, I'm sure all of you have heard about 5G and all the hype surrounding it. But as 5G is rolling out, the discussions on what 6G or the next G is going to be are already starting in industry and academia and research cycles. Given that there is about a 10-year time period between when the discussions first start and when the next generation gets implemented, questions about does quantum have a place in 6G, and if so, what is it? This is the right time to start having those discussions. So I'm very glad to have Andrew with us to tell us some of his experiences in quantum communication and networking. Preeti gave us a little bit very condensed background of Andrew's, but Andrew, why don't you tell us a little bit more about yourself, your career path, and how you became involved in just quantum information sciences at Toshiba? I don't think we can hear you yet.
So my sound, can you hear me now?
Yes, we can.
Okay, for once I wasn't on mute, it wasn't me. Yeah, so it's a pleasure to join you today, and I'm sorry that I can't be there in person. There are some travel restrictions actually for UK citizens to the US, which meant I couldn't join you. But yeah, it's a pleasure to be here and to have an opportunity to chat about these things. So I guess I often introduce myself as a quantum physicist or a quantum engineer, depending on who I'm speaking to at the time. And yeah, it's interesting to reflect on how I got here. Actually, I come from a farming family in Northern Ireland, and none of my family were physicists. In fact, I don't think any of them went to university in my parents' generation even. But when I was growing up, I was kind of fascinated by how things work and trying to explain the world around us. So that's what stimulated my interest in physics. And I guess all through my high school years, I always thought that I'll go to university and I'll study physics because that's just something that I wanted to do. And so it came to pass. So I went to London to well known as a good place for nightlife. And those were my two main interests at the time, physics and nightlife. So London seemed like the ideal place for that. Then that led on to doing a PhD in physics, also in London, actually. I did a PhD in semiconductor physics. I remember at that time I was kind of, I was interested in the quite mathematical and maybe slightly like mathematics itself, quantum mechanics, electrodynamics, quantum optics, and things like that. And at that time, there was an emergence of new types of semiconductor, which were basically heterostructures, which were thin layers of different types of semiconductor. And it seemed at the time that you could use quantum mechanics to model the properties of those semiconductors. So I was really fascinated by that and decided to do a PhD in that area. And I guess that's what got me into all of this quantum stuff. After that, I did a postdoc in Germany for a few years. And then later I moved to work for Toshiba.
So we hear a lot of different terms related to quantum. A lot of the focus in the discussions in the morning was about quantum computing. Quantum cryptography is another area where quantum technologies have been applied, and now quantum communication. Can you just give us a little bit of a description about how these different applications of quantum are similar? How are they different? And what are the unique challenges in some of these?
Sure. Yeah. So quantum communication is basically just communication using quantum states. So things like single photons, for example. So normally in a communication system, we would encode the information on pulses of light. For instance, in one encoding scheme, a bright pulse of light might mean bit 1, and a weak pulse of light might mean bit 0. And typically those pulses might have 100 million photons in them, that kind of level. In quantum communications, what we're doing is we're turning down the intensity of the light source so that on average, the pulses contain around 1 photon per pulse. So each bit of information is encoded on a single photon or a particle of light. And that, of course, is a very inefficient way to communicate in the extreme. In classical communications, we normally talk about bit rates which are hundreds of gigabit per second. The current state of the art is around 800 gigabit per second encoded on a single wavelength, for example. Whereas in quantum communications, because it's so much less efficient, we're talking about megabit per second rather than gigabit per second. But the really interesting thing is that if you communicate using a quantum state, quantum theory tells us that if anyone tries to intercept that quantum state, that changes its encoding, and that change in the encoding can be detected by the system. So it gives us a way to test the secrecy of the communication. And that's something that you can't do in any other way. If you like, quantum messages, or messages which are sent by a quantum method, self-destruct if somebody else tries to read them. And it's an incredibly useful thing. Like I say, there is no other method to fundamentally test the secrecy of a message. That's what quantum communication allows us to do. And the very interesting thing that we can do with it is to distribute secret keys, digital keys that are used for different things in cryptography, like encrypting information, for example, or for authenticating information. So quantum cryptography is really about using quantum communications, single photon communications, for doing different tasks in cryptography. The main one is quantum key distribution. Another very important primitive is quantum random number generation. So we need random numbers for many tasks in cryptography, and quantum effects are very good for that. Quantum measurements are inherently unpredictable. So quantum cryptography is also very good for random number generation. There are also some other primitives as well, like quantum digital signatures and position-dependent quantum cryptography and things like that. But the main application is quantum key distribution and quantum random number generation. And then finally, quantum computing. Well, that's about, information processing using quantum states. So it's a much more difficult technology because quantum communication is essentially a 1 qubit technology. We're sending qubits one by one, whereas quantum computing involves interacting many different qubits together. And in the future, all of these technologies might converge into what's called the quantum internet, which is able to do an even wider range of things. So not just cryptography, but can also build very powerful quantum computers, which can solve difficult computational tasks in the future.
Thanks. That was an excellent, I think, description of these 3 different ways of using quantum technologies. If I may just follow up on what you just said, you mentioned the difference in data rates that you get on a classical communication channel, but which is not very secure, and a quantum channel which is very secure, but does not have that same data rate. So how do you envision in the future the best of both worlds, a really high, gigabits, maybe even terabit per second line, which is also secure? Is that something that one can imagine will happen?
So at the moment, we only use the quantum communication for sending the digital key, and then a short key can be used for encrypting a large volume of data. So with the AES encryption algorithm, for instance, we use keys which are 256-bit long or 512-bit long, but then that can be used for encrypting megabit or even gigabits of data after that. So we only need short keys actually for encrypting much larger volumes of data. So the idea is that we can have a communication channel where the data will be sent in conventional form, but encrypted using quantum keys. And the quantum communication is done just as a wavelength over that optical fiber. So we're using wavelength divisional multiplexing, different wavelengths of light, basically, and some of the wavelengths carry the data in encrypted form at really high bandwidths, and some of the wavelengths carry the quantum signals, which are used just for forming quantum keys and potentially for doing other quantum cryptographic primitives as well.
You've spent most of your career at Toshiba, and can you explain a little bit as to why Toshiba is pursuing quantum? What do they see as the future, and how Toshiba interacts with the communication industry, with academia, in the work that you do?
Yes, so I've been at Toshiba 28 years, actually, which is it's a frighteningly long time. Actually, I joined just after the lab was set up here. It seemed like a great opportunity at that time. So in the early days, Toshiba were very interested in quantum effects in semiconductors. So as you know, semiconductor devices were getting smaller and smaller, conventional silicon devices, for instance. And they could see a time where the length scales would become comparable with quantum length scales. And then you would start to see really strong quantum effects in these devices. So at that time, actually, people were worried that maybe these semiconductor devices would no longer work as they've been in the past, and it would no longer be possible to scale this technology to smaller length scales and to build more powerful computer chips in the future. So at that time, actually, there was an interest in replacing silicon with new materials which could possibly go to smaller length scales. Now, as it turned out, in fact, engineers found really clever ways to extend the lifetime of silicon. So the material that came after silicon was just more silicon, in fact, as it turned out. Although those new materials like gallium arsenide have made really strong contributions in the optical domain for optical devices. So that's where we started. We started studying these quantum effects because we thought they might be a nuisance. But after doing that for several years, actually we realized that maybe we could do something useful with all of those quantum effects rather than regarding them as a nuisance which might stop our semiconductor devices from working. Maybe we can do something useful in the quantum information domain. So using them for cryptography in a communication system and using them in a quantum computer. That was around 2000 or so, when there were lots of interesting and very stimulating ideas about using atomic systems for quantum information. At that time, we started to think, well, maybe we can use semiconductors for similar things as well. Maybe we can build quantum computers out of semiconductors, and we can build quantum communication systems out of semiconductors. So that's really where it all started. And we've been doing research in quantum information for around the last 20 years or so, doing many interesting things along the way. But the most interesting thing which has developed recently is we've now released a product for quantum key distribution. So after this very long journey of development, finally now we're releasing quantum key distribution as a product onto the market since last year. And Toshiba have big hopes for that in the future.
How do you collaborate with the telecom sector, or are these standalone products that you just sell to the sector? Is there any joint effort? David mentioned that there is going to be this fiber optic link that connects Argonne Fermi and University of Chicago in Chicago. How do you see some of these test beds, if you may call it, helping the work of companies like Toshiba in this space?
Yes, we're working with several telcos around the world at the minute in deploying the technology. So they really have an interest of deploying QKD on their networks and then using that to basically offer a new service, offering quantum security services on top of their network. So we're working with Verizon in the US. In the UK, we've also done a lot of work with BT as well, trialing the technology. We've made several use cases of the technology along with both Verizon and BT. And also in Europe, we're working with several telcos there as well, with Deutsche Telekom and with Telefonica. And again, we're involved in a European project, which is called Open QKD, which is about building test beds for quantum communications and then demonstrating different applications on top of those test beds.
Great. So just to carry this thought a little further, this is a technology that's being pursued across the world. There are many countries that are doing this. A couple of years ago, China had this demonstration of a quantum link over a satellite. So as you look towards the future and all the various modalities that quantum communications could be deployed in, there's fiber, there's satellite. Can you talk a little bit about how you see this technology scaling up to different means of communications?
Yes, actually there's tremendous interest and investment in this technology going on around the world. You mentioned China, and they've made some really incredible investments in this area over the last 5 or 10 years. Someone told me actually that it was on the Chinese Economic Development Plan as like one of the top 5 areas that the Chinese government were investing in the quantum communication field. So they built really large-scale communication networks in China, fiber communication networks, a 2,000-kilometer backbone, which goes from Beijing to Shanghai. They've also launched a satellite, as you mentioned, doing quantum communications between ground stations in different parts of the world. There's also a lot of investment going on in other places as well. So the UK have had a quantum technology program, which has been running now for 7 or 8 years, I believe. And they've made an investment of over £1 billion during that period across the quantum domain in quantum computing and simulation, sensing, and communications. Also, the European Union has a big program as well. So they have the Quantum Flagship at the moment, which is a €1 billion program to support quantum research. And they're building what they call the quantum communication infrastructure, whose goal is to build a quantum communication network which reaches right across Europe, actually. So it's a very ambitious program too. And I'm also delighted to see that there's now more investment going on in the United States in the quantum information science area. So I hope that we see more contribution from the US in the future too.
As you look at these investments and the directions that these various companies are going in, this was a point that was raised in the previous panel as well. Do you feel that the workforce development is keeping pace with the technological developments as quantum becomes more, I won't call it mainstream, but it finds more applications in domains such as communications? There needs to be people from both of these fields that start talking the same language. I know that when I've spoken to a lot of quantum physicists, the discussion very quickly goes into entanglement, and whereas the communication engineer just wants to understand what does the channel look like if it's a quantum channel. And so there is a lot of educational gaps that need to be filled. Do you feel enough is being done in the UK as well as elsewhere in bringing engineers from other domains that would use quantum, the basic quantum physics, as a tool to build on? Or do you feel that that could be improved a bit?
I think we definitely need many more people who have relevant skills in the future. There's definitely a skills shortage in the quantum area at the moment, especially in practical skills. So I think you're right. We need to attract more engineers into that area. Engineers who have skills in digital electronics, software, and photonics, and who are also interested in applying that to quantum information systems. If the industry is going to expand in the way that we hope it's going to over the next 5 years or so, we're going to need a lot more trained people to be able to fill those positions. And that's why it's great, that you have an organization like the Chicago Quantum Exchange, who's involved in training more young people to come into this field and take an interest in quantum information science. We certainly fully support that.
In addition to just telecom as an industry that benefits from quantum communications or quantum technologies, are there other industries that you think could benefit hugely if these technologies were to become much more available?
Yes, I think so. I mean, I think eventually all industries, and even going beyond industry to commercial, residential customers rather, everyone should benefit in the end of the day. So one reason why we need quantum cryptography is because eventually we're going to have a large-scale quantum computer, and that will break a lot of the algorithm-based cryptography which we use today. Many of the techniques in public key cryptography can be solved efficiently using a large-scale quantum computer. So, people predict we'll have a large-scale quantum computer in 10 years, maybe. Some optimists say 5 years. Pessimists maybe say 20 years, but for sure it's coming. And in those days, we definitely need technologies which are safe from attack by a quantum computer. So eventually it'll be everywhere. But even now, actually, we need to start implementing quantum cryptography as soon as possible. And that's because for any information which has a long shelf life, let's say you have secrets like financial records or medical scan data that you'd like to remain confidential for 5 years or 10 years. Today, it's very easy to store encrypted information, and within the next 5 or 10 years, it's going to be possible to decrypt that information when more powerful computers become available. So any industry that has information with a long shelf life, and that could be in the healthcare industry or financial industry. Also governments, I think, also have information that they'd like to keep secret for decades, if not indefinitely. That kind of information really has to be encrypted with quantum safe techniques today. So eventually it'll be everywhere. But I think in the very near term, it'll be those industries that have information with a long shelf life, which will need to implement quantum cryptography as soon as possible.
That's very interesting thoughts. You're saying that we should be actually encrypting everything using quantum encryption today, and we don't have to wait for the technologies to actually evolve to the point where they are easily decryptable. But let's just go and encrypt it for the future.
Yes, it would be too late to wait until a large-scale quantum computer is developed. We really have to start implementing the technology now. Because there is data which has a long shelf life, and we need to keep it secret for many years, but also because it takes a long time to deploy these new technologies on a large scale. So it's really something that we have to start now.
So that's fascinating to think about. Do you know if any of these industries that you mentioned, finance and healthcare, are already thinking in the long term about doing this, or is this still something very, very new for them and they're just focused on the here and now?
They are certainly interested in the technology, and we've been doing trials with several financial institutions. I can't really go into details about that. Also with hospitals as well. And of course, we know that government organizations are very interested in the technology too, and are building these test beds as demonstrators of the technology.
So let's turn a little bit to policy and regulation. You brought up the notion of a quantum internet, which we all know that the internet as we know it today is heavily regulated. There are a lot of policies governing what happens, how they get deployed. Do you see the need for anything different to happen once the concept of a quantum internet becomes more widespread? And how do those discussions get started? Is it too early, or is it the right time?
Yeah, I think there is a need for some regulation of the technology. So one very important issue at the minute is, although quantum cryptography theoretically is perfectly secure, of course, it really depends how you implement it. You have to implement it in a secure way. So it's important to have a process which ensures that it is implemented securely. And that's normally done through third-party test labs who test the security against certain standards. Those test labs exist for conventional communication technology, but not for quantum technology at the minute. So one very important thing which has to be developed in the coming years, I think, are security certification test labs for quantum security products. There is already work ongoing in that direction. So there's a lot of work being done by the standards organizations such as ETSI, which I've been involved in for many years. They're making standards for a protection profile for quantum key distribution technology. Also, ISO are doing some work on developing standards for common criteria certification of quantum cryptography systems. ITUT are also making standards in that area too. The next step is for those standards to be adopted by test labs and for them to set up test programs for the technology. And again, some governments, so the European Union, for instance, are taking an initiative in doing things like that. So I think we will see those things emerge over the next 3 or 4 years.
Right. One of the other, main components of an internet, as we know it today, is a repeater. And from my limited knowledge of quantum repeaters are not there yet. So does that mean that we may need to rethink the architecture of the internet as we know it today, or do we keep the architecture the way it is and then work, on building a quantum repeater that provides the same functionality as a regular repeater today? Do you have any thoughts about how we should look at an architecture in the future?
So yeah, I think one of the big technical challenges at the minute is extending the range of quantum communications. So just like conventional communications, quantum communication suffers from loss. You get an order of magnitude attenuation in the signal for every 50 kilometers of fiber, for example. But as you said, in the quantum domain, we don't yet have a quantum repeater like we have in the classical domain. And that means that we can't build very long distance quantum communication links. So what I'd say about that is, first of all, commercial quantum communication systems, our system, for instance, has a range of around 175 kilometers or so. So the technology actually has improved to the point where you can start to connect together the nodes that you would have in a typical network. So in the UK, for instance, the principal nodes of the telecom network are separated by around 50 to 100 kilometers. So already the technology is at a scale where we can link together those nodes in a secure way. But for making longer distance links, like transatlantic links, for instance, there we need new technologies like quantum repeater technology. So there's a lot of research which is ongoing at the minute. We're collaborating actually with the University of Chicago in some of those areas. And I'm sure we'll see a lot of progress coming in those areas in the coming years. There's also satellite quantum communications as well. So it's possible to do QKD between a ground station and an orbiting satellite. And that's a way of connecting together these different fiber networks in different parts of the world to make a truly global network. And that's possible even at the minute, I think. So it's certainly technically possible for us to build a quantum secured global network at the moment. To turn that into a quantum internet with quantum repeaters, yes, there's a bit more work to do in that, and we'll have to develop several new devices like quantum memory and quantum repeaters and sources of multipartite entanglement. But there's lots of progress going on in all of those areas at the moment, and I'm sure we'll see much more progress over the next 5 to 10 years.
We have about maybe 8 or so minutes left. Are there any questions in the audience, or anybody, if they have any questions online? We can take them at this point. If not, we can continue the conversation for a few more minutes. Okay, so if I may, just build up on a previous question that I had asked you, is, one of, and this is not specific to quantum in particular, but in general, the previous panel mentioned it, David mentioned it, this is a field that requires collaboration. It requires no one company, no one university, no one entity can do this. And so how do you see, in the specific field of quantum communications, how do you how do you go about engaging, say, the electrical engineering or the computer science departments of a university with the physics departments, where a lot of quantum is still sitting in physics departments and universities, at least in the US. Do you have any ideas of how these cross connections can be improved, made so that the collaborations can continue?
Yeah, quantum information science, clearly it's very cross-disciplinary. I think one good way is in a lot of places we see institutes and organizations which bring together different university departments to work together on common problems. I think you're doing that in Chicago very well. Also in the UK and in Europe, there are also organizations like that in universities that bring together the different departments. And they're great to collaborate with because you get a really wide range of experts within those fields. And yeah, we have productive collaborations in several places with those sort of organizations.
And from the academic point of view, and a lot of students in the audience, how are there programs, or has thought been put into creating programs that actually cross across departments? Because there are folks who are working on quantum compilers or quantum cryptography who've never actually worked hands-on on a quantum device, and bridging that gap I think is important to actually allow this field to expand even more. Do you have any thoughts? And in Toshiba, how do you deal with this? How do you do your hiring in terms of getting people with the background you're looking for?
So yeah, I think definitely it's great if students can get a broad background in all of those different disciplines. So we like our students to have some quantum training, that's good. But equally important with that are practical skills, like in electronics, for example, and in photonics. So we often look for engineering graduates, even without quantum training, because we can teach them the quantum things on top of that practical background too. So I think it's great if students have training in problem solving and in making practical systems. Basically, we find that those sort of students have really flourished in the environment that we have here.
And how about a lot of this was alluded in the previous discussions too, is that there is a lot of investment that is needed to set up a lot of these platforms, and a lot of it is in industry. And oftentimes industries are not that open, companies are not that open to opening up their platforms to research. And when I mean open it up, to the extent that students in an academic environment can actually work on their platforms. How do you think that can be improved in terms of, I understand that companies have IP issues, but how do you negotiate these kind of collaborations better?
We've certainly collaborated with lots of universities over the last 20 years in the quantum information area. And in fact, we have lots of PhD students who studied for their PhD in our lab here. We probably had, well, I think over 100 PhD students during that time. And the UK does have programs which support that. So there are funding programs for PhD studentships which are partially funded by EPSRC and partially by industry. Industry basically proposes the project, but normally those projects would be based in a university with a secondment in the industry, or sometimes they're based in industry as well. And like I say, we've had plenty of examples of that in the past. So I think there are good ways to encourage collaboration between industry and university, and certainly we find that that's been very beneficial. So lots of the best research that we've done has been done by students, actually, and they've brought lots of innovative ideas to what we're doing. We've often hired those students as well at the end of their PhD, and they've become employees with us. So and I think at the same time, the students have also benefited too, because we have very good research facilities here. And clearly that's something that they appreciate. And they get to see a different side of things, I guess, from academia, also by doing some work in industry too. So I think it works well for all parties.
Question?
Yeah, I have a question. Just piggybacking on your question, Andrew, do you see a role for startups in this ecosystem? Like we talked about how industry and researchers can work together. Do you see a role for startups to advance the field?
Yes, startups are important, I think. I think they fill the gap between university research and things being taken on in larger industry. So certainly startups can do very innovative things, and at the minute in the quantum information area, we see an incredible number of startups out there. It's maybe because there's a lot of funding at the minute, but certainly, if a significant fraction of those startups survive, I think the industry has a really rosy future in the future.
I guess this is the right time to ride the quantum wave as far as it takes us. Sometimes the challenge can be to keep the momentum going and to make sure that the funding stream and the support for this, because this is such a radical departure from our current technologies, to keep the momentum going takes some time.